Welcome back to another episode of Python Programming from Beginners to Programmers. We've been discussing this subject on data analytics using Python Pandas library, and we've made quite a big progress from initially not knowing anything about it to understanding that there are two kinds of objects provided by pandas. The more important one is the data frame and the accessory object called series, which is basically a snake-like array that can either act like a column vector or a row vector, right? So we talked a lot about how to read and write or get and set the values of the cells to sort of locate the interested cell positions by index labels and column labels or by content filtering. And we also learned the technique of this magical touch of programmatically transform the contents in a systematic and very compact yet clear manner. So in what follows, we want to talk about how to clean up data, right? And specifically, we are going to sort of break this fuzzy goal of cleaning up data into three uh, broad categories of problems, right? Problematic data points where we typically want to clean them up, get rid of them, replace them, delete them, or whatever it is. Okay, so we want to deal with them. The main idea is that garbage in, garbage out. So if we don't have data cleaned up up front before we start to process, like finding the average, finding the total, we will end up getting very problematic outcomes like illegible outcomes, null results, errors, and choked processing halfway, and the most dangerous form of garbage out is that no error occurred. Okay, you actually get some sort of a report, you actually get some sort of a numerical outcome, yet it is totally false, it is totally wrong. So that is the most dangerous form as far as I have experienced, and because there's no indicator at all. And so to prevent and reduce the risk of experiencing those without even an error message, right? And then acting on the outcomes, right? Rather to make maybe it's to make your own personal decisions. Maybe it is to decide for certain investments. Maybe it is to make national policy, university policies, organizational policies, and that would be very dangerous and disastrous, right? So on that basis, we really want to treat errors and noise with a lot of respect and with a lot of investigative desire. All right. So the three categories that I talked about. First category is quite obvious. It's quite visible. It's called NaN or null or NA. So anytime when you print out a data frame, you see a NaN, you see a null, you see a NA, that would be this category. So I just collectively called it NaN. All right, the documentation in Panda says NaN or NA or null, it's the same, right? So we'll treat it as the same. And you can think of this as a kind of a nuisance, right? It is not desirable, but then it's very important because, for example, we might want to indicate that user did not enter any value for the age. Now, age is integer probably. You can store it as an integer. Um, but user did not enter any. Now, do you fill it as 0? Which is wrong, right? Because if you take the average, it's going to like bring down the average a lot. So NaN serves this sentinel purpose, which is a valid integer type, not a valid integer value, but a valid integer type. So it can be stored in any place where an integer can occur, or any place where a float can occur, but its value is NaN, not a NaN, yeah, so not a number. All right, another category that we want to think about is noise. So sometimes data looks right, feels right, but it's got a lot of like trailing decimal places that are annoying because when you print it out, it's no longer a very nice 2, but 2.0001. It's not a nice compounded investment return amount like $1,025, but becomes $1,025 no, sorry, $1,024.99.9999 cents. So these are the noise that come in, and if we are not careful with handling them, they can be problematic. All right, and sometimes it's the other way around, where there are zeros, and especially more in scientific calculations, mathematically oriented calculations. But remember, perhaps you're applying pandas in business applications. You might think, oh, scientific mathematical calculations are not my problem, but it could have been also that you are using visualization libraries, drawing packages, and you might be required to compute or pre-compute some of these data to fit into the library package. And that is again where mathematical and scientific noise problems hit you, right? So what are these problems? Things like if you have a location, a cell position where it is containing floating point, if it has a zero, a clear zero, it would be a problem. However, if you, instead of zero, fill it with a bit of zero value, like 0.001, then because it is very close to zero, it won't affect the accuracy of the result, but then it will completely avoid singularity and all that problem. So these are the, inverted kind of problems where you actually want a bit of noise to reduce the sort of impact outcomes. So we'll examine this a little bit more. And the third category of data problems that we want to discuss will be type errors. Now this is very much a programmatic kind of error. In other words, it's not about the source, it's not about the measurement, it's more about a very Python related issue, like are you storing 123 as an integer, or a floating point that doesn't have floating point values, or a string. you know Sometimes data comes in because you're inheriting data from other sources, and the library package that you use automatically converted the integers to strings, because you know while scanning throughout the entire data set, it has decided that it is best to use string. And pandas has the ability to do that as well, to read in data sources from various kinds of files. So when you encounter those and you try to add numbers to strings, you will have a lot of problems, right? So these are the type related issues that are, how should we put it, annoying, right? You need to get rid of them. You need to make sure that you massage the types properly, so that downstream you can do plus and average, and doing all kinds of statistical analysis nicely. Okay, so back to our three categories of problems to deal with in the data. Now, you might say, let's come back to our NaN issue, right? So NaN is a problem that we will encounter, but you might say, I just wouldn't really purposely do that. I won't do that, right? I won't purposely insert a NaN or null, and you are right, nobody does. Uh, the issue with generating nans come from our desire to properly handle the data and analysis. So for example, we might do a filter. So recall that our DF3 was having some sort of integers being stored inside. The moment we try to filter it, give me those cells whose values are less than 9, right? So by now, I hope you can understand uh, the this pandas way of expressing the filter. So df3 less than 9 gives us a data frame mask, true whenever the cell is less than 9, right? And then we pipe it into the selector against the base data, which is all the integers present in df3, and then we get this. But pandas realizes that for values that are equal or bigger than 9, right? So here, 0, row 0, CD, and row 1A here. What are you going to fill? You cannot replace it with a default value of 0, nor 1, nor -1, nor infinity. They're all not correct because when you average them, it's going to give a totally disastrous outcome. So the best way is to put it as a a floating point value, but not a number. So this is exactly what Nan is. And by the way, Nan is not created by pandas, not by Python. Nan is totally built into the DNA of your computer chip. All right, there's this part that's called floating point processor, and the processor in its DNA understands what is a NAN. All right, so NAN is defined down to the hardware wire level, and it obeys international standard, the IEEE standard on how to represent numbers. So these are the representations that represent non-numbers. That's why they're called NANs. So NANs will not create exception handling that will slow down your computer processor. So this is really good because down to the DNA, your hardware does understand what is NAND, and it will kind of like skip past, much like Excel. You know, you can do an average of all numbers where some cells are blank, and it will not average against those blank cells, right? It will not count them and then affect the overall average. So NANs are really nice because they are treated correctly, right, down to the mathematical level. Okay, good. So because we will tend to generate NANs, all right, in our normal, usual form of processing, like extracting a filtered content and assigning to DF7, and thereafter DF7 will have NANs. So what are we going to do about it? So depending on the context, we judge what is best. But now we want to answer a few questions first, right? So I have the questions and the results, and I using the colorful picture that I have here, we will go through the answers first. But of course, we definitely need our hands-on to feel the situation better. Okay, so all the data frames come with this function called isNA, right? isNA. isNA is a form of content filtering where df7.isNA will return to us a mask based on df7's shape, and where the cell is an NA, it is a true, and the cell, if it's not an NA, is a false, right? So it's great. So dot is NA gives us the equivalent size here, and then these will be false, false, true, 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 false, false, false.